All right. So what you see now is ozone layer being thinned. Okay, and we've been measuring it now with satellites since the 1980s. So our satellites have been very useful. But the satellites found something kind of bizarre. Not only do we have a thinning, but we have a few other problems which the satellites discovered. All right, here is our data since the problem was discovered in the late 1970s that CFCs were destroying the ozone layer. You can look at the Dobson unit measurements. At the top is the Dobson units for the ozone layer, and the bottom chart is the UV index at noontime during those same years on average. And you can see very simply as the ozone layer thins and the thickness of the ozone layer drops, the Dobson unit numbers drop, the UV exposure to the surface increases. And that's where you run into the problems. And it's just proof that, yes, a decrease in the ozone shield is going to increase UV light at the surface. A 1% loss in the ozone layer results in an increase of ultraviolet radiation of 2% at the surface. And that's what we found out. And what we found out since the late 1970s, that we've seen a total of 4% increase in UV light at the surface of the Earth on average. But wait, something weird happened. They found an ozone hole over Antarctica. Now, we've always known that in the Antarctic's late winter, early spring, that ozone layers, or the ozone layer became very, very, very thin. And so there's kind of like a natural hole that occurs in the ozone shield, which we don't have to explain the natural occurrences. We have to focus more of our energy on what we've done to make that worse. So we have this ozone hole or thinning that occurs in late winter, early spring in the southern hemisphere. Then, once we started taking data from satellites, and a British team doing research down in Antarctica, they found that down in Antarctica, there was almost no ozone whatsoever. And not only was it just over Antarctica, but as you can see in this diagram here, it's spread over a large area, and not only encompasses Antarctica, but has spread over the ocean as well. And it's almost touching the bottom tip of South America. A lack of ozone down there means that UVC can get through. And here's where it becomes very important, because that UVC can penetrate the water and destroy the living cells of the microorganisms living in the cold Antarctic waters, destroying the bottom of the food chain. And once you destroy the bottom of the food chain, you all know that the entire food chain can collapse. So there has been real concern. But the question is, why in the world would the ozone hole be over Antarctica and not over like the United States, where all of the CFCs were being made? Well, there's a reason for it, and it's quite complex, but it's based on two things. Number one, that there's something called a polar vortex, which means that the winds around the South Pole spin in a circle, and what that does is it sucks in the CFCs from around the world into that polar vortex. And then when the air gets cold, that air starts to sink, and this is in the wintertime down there when it's getting colder than normal, it starts to sink, and when it sinks, it cuts off the access to the atmosphere around it. So basically what you're doing is you're trapping. It's like a trap for CFC molecules. So you have these polar vortex winds, which act like a whirlpool and pull in everything and then just traps them there. And then the second is probably the most important. All right, and it's called polar stratospheric clouds. These are clouds that form in the stratosphere where clouds shouldn't form. They can only form when the temperature gets cold enough for nitrous oxide to actually crystallize and form these ice crystals. And this only can happen in the coldest of coldest places, being Antarctica. So when these polar stratospheric clouds form, they act almost like a magnet to pick up chlorine, and they form it they hold it in a form that's kind of stable, right? And that's chlorine dioxide. So it kind of sits on these cloud particles, these ice crystals, and just carries them around, chlorine in a very stable compound, all winter long. Then in late winter, early spring, the sun starts to reach the South Pole. And when the sun reaches the South Pole, you start getting UV light. When that UV light hits the chlorine atoms, which are Cl2, all right, it breaks it into individual chlorine atoms, which are now highly reactive, and then they start destroying the ozone. So the polar stratospheric clouds are like the holding tanks for the chlorine all winter long until late winter, early spring, when they can break apart in the UV light and then start the process of destroying ozone. Now remember, late winter, early spring in the southern hemisphere is the exact opposite as it is in the northern hemisphere. Okay? So we're talking about seasonal changes, but we're talking the depletion occurring, or the ozone hole occurring roughly August through November, which is late winter, early spring for them. Okay, so that's when we see the ozone hole literally open up because of the polar stratospheric clouds and the polar vortex winds. Now remember, it's a natural occurrence, but we just made it worse, lowering the amount of ozone to almost zero and increasing the size of the hole. In fact, the ozone layers were so low, satellites, when they first took measurements, thought there was something wrong with the computer, that it wasn't somehow registering the ozone over Antarctica. And later on, they found out that no, it was registering it correctly. There was none. All right, so here you can see as the year goes on, as the temperatures dip, the dotted line shows you the temperature at which these polar stratospheric clouds, or PSCs, can form. And when it gets below that, you can see right after around December, it gets cold enough, okay? And then as you move into the spring, all right, temperatures start to get just above that, and it starts to disappear. But these are polar stratospheric clouds in the northern hemisphere, where this process can also occur, but nowhere near as extensive as it is in the southern hemisphere. So, looking at the different views, different years, you can see how the ozone hole has gotten deeper and bigger, all right, because the first picture in 1983, the first satellite view, you can see that it's only light blue. By 1997, you can see it's deep, dark purples, all right, and larger, okay, almost touching South America. And that was a big concern. What else does ozone depletion do? Well, there's human impacts. I think you all know. As we decrease the ozone, we increase the UV light on the Earth. When we increase the UV light on the Earth, we have increased skin cancer, cataracts, which is the scarring of your eye. Plants, we have reduced crop production because, remember, this UV light can damage cells, even UVA and UVB. So if you increase especially UVB, you're going to have damaged cells. It reduces crop production. And then you have a lower net primary productivity. And this is especially harsh in the oceans, where the algae is much more sensitive to UV light. And you reduce that primary productivity, reducing the food chain, all right, reducing your biomass pyramid. Also, UV light can cause mutations. And the loss of ozone means more UV light at the surface, which unfortunately is a positive feedback for climate change, causing additional warming, because remember, the Earth absorbs that UV light, turns it into infrared. Well, if more UV light reaches the Earth, more infrared is going to be made. More infrared can be trapped by our troposphere. So you could see the huge consequence of creating this chemical called CFCs. So what do we do about it? Well, we created a few laws. And it was kind of interesting in 1987, the Montreal Protocol, where countries got together to decide what to do about it. This was 10 years, almost 10 years after they discovered that CFCs were destroying the ozone layer. So in the Montreal Protocol, It was actually a United Nations meeting. In Canada, by the way, obviously, because it's in Montreal. 24 countries agreed to cut back on CFCs. So it was the first time we had a real international treaty. And then they got back to, and by the way, they said they would cut back CFC production, but they said only 50% by the year 2000. And that was the Montreal Protocol in 1987. So then they got back together in London a few years later when more evidence came in saying that the problem's even worse than they thought. All right, so in London, I'll put it up here for you to help you out a little. In London, they made an agreement, okay, this was 3 years later, that after new research, instead of 24 countries, they upped it up to 93 countries, agreed to stop producing CFCs completely by 2000. And they said they would move the timetable up if alternatives became available, economically viable alternatives, which is what happened. So it was quite a victory. So all the developing countries decided to stop producing CFCs. And then in 1992, just a couple years later, they got back together again in Copenhagen, where they made an agreement, all right, that going all the way up to 140 countries were in agreement not to produce CFCs, with only a couple exceptions, all right, for some of the developing countries, mostly because of their desire to have refrigerators. But so the Montreal Protocol started all off, which they said they would have a 50% reduction by the year 2000. Okay, and then a few years later they got together in London, made that a little bit stronger, and then a couple years after that they got together in Copenhagen and gave us our current policy. What does this all mean? Well, because this was one of the few success stories where we actually agreed to stop using CFCs, okay, we made some great progress. So we're replacing CFCs with alternatives, one of them being HCFCs, okay, or propane to be used as coolants. And the other thing is we collect all CFCs that have already been produced, and we just keep reusing them over and over and over again. So if you have an air conditioner, you have CFCs in your air conditioner. As long as your air conditioner works, the CFCs remain in there. Once the air conditioner is done, the person who recycles it will take the CFCs out, sell it to another company who will put them into another air conditioner or refrigerator or whatever. And we just keep reusing them without producing any new CFCs. Any additional coolants that we need has to be an alternative. And that's what we've done. And we've been very, very successful. So the reduction has been successful. All right. The United States has taken the lead, and we expect a nearly full recovery by the year 2050. So for now, we have to suffer for the CFCs that were produced 20 years ago. And that's what's happening. In the future, because of law, they don't have to worry about it anymore. So what are we concerned about? Well, our biggest concern is with skin cancer. Increased ultraviolet light penetrates the skin. All right, UVA and UVB reaches down into our skin cells and causes mutations, causes sunburn, which is your skin reacting to too much exposure to UV light. At the lower layer of your epidermis, you have a series of basal cells. Those basal cells are the ones that produce new skin cells. Well, if you damage the basal cells, you are going to create damaged skin cells. And so your body tries to protect the basal cells, all right, with the upper layers of the epidermis, all right, and the goal here is to block UV light from reaching the basal cells. If basal cells become damaged, they produce damaged cells. At the same time, you have basal cells that have special function. These cells are called melanocytes. The melanocytes are cells that produce that pigment that we call a suntan. That darker pigment that's stimulated, the production of that pigment is stimulated by UV light. When UV light hits the melanocytes, they start producing the pigment. The pigment then gets into the cells. As the cells work their way up to the surface of the epidermis, that's when those darker cells start to appear, and you get what we call a suntan. That suntan then is supposed to protect you, at least as much as possible, from UV light. The problem is sometimes those cells that are produced from the basal cells are produced incorrectly, and you start to create cancer. Melanoma is the most common and the deadliest form of skin cancer. All right, usually in the form of a mole or something like that, darkens and grows. Okay, so these are just some pictures for you to take a look at. These are skin cancers. This is what's happening. If you are concerned whether a mole or freckle on your body is skin cancer, the ABCD method that you see right here is the way to figure it out. All right, it gives you a good idea if you should get it checked out or not. All right, but the most common, the melanoma, is something we have to watch out for. Okay, and there are other types of skin cancers that are not deadly, but melanoma is the deadly form. So that's what we have to live with because of the CFCs that were produced years and years ago, destroying our ozone layer. And with all that good news, we will end the lecture now.